Yeah. So, good morning. Let me begin today's session on wind energy system. In fact, a similar session I had delivered earlier also. So that's why it is saying October. And one of my PhD student has helped me in gathering the information. So with this, let's get into for one of courses and you can see some of the lectures. So on the left side, you can see about mainly about solar thing, and on the right side, I have done something about mathematics and wind power, wind energy system economics and mathematics and scenario. So these videos are already available. So I request you to have a look at it. So also, what these things are made couple of years back. So when you go for what is the present scenario, so that may not be there. So that's why today I'll be covering the latest information of present scenario. So yeah, so let me continue. So this is the brief outline. Introduction, mathematics of wind energy, global energy scenario, and Indian scenario. Now here, this topic of mathematics of wind energy, usually it's not covered. So that's why there is something interesting. It's a kind of application of mathematics to the field of wind energy. So it will be quite interesting. So I thought that also I will be incorporating. So so that's why I've included that. But before going to the topic, I would like to first begin by first speaking about the scenario. So let me just, I'll open the another file. So let me open that file and then I'll share with you. Yeah, so here I have just, it's not like any slides I prepared. I just prepared some bullet points on some of the points. Okay, so pertaining to wind power scenario. So anybody who is entering, you want to understand about wind. So at least first they should know about these topics. Okay, so so what are these topics? So first one is wind power generation capacity in India significantly increased in recent years. And as of 31st August 2020, the total installed wind power capacity is 38 gigawatt. And this is fourth largest installed wind power capacity in the world. And in our country, the total renewable capacity is 89 gigawatts as of 31st August. Okay. So again, this information is slightly couple of months old, but this is as of 31st August. If you want to know the latest information, so one of these sources, so let me open that. So I'll go to CEA website. So if you go to cea.nic.in, okay, so this website is the Central Electricity Authority website. So I hope you are able to see my screen properly. Actually, there is some problem with my power supply in our office. So I am not using my laptop, but I am using my this mobile phone itself to present. So in case if there's any difficulty, please let me know. So in this website, Central Electricity Authority, I request everybody to regularly keep checking this website. It has daily reports, executive summary, install capacity, power maps, all these things that you see here. And on the top also menus are there. So for example, if I go to executive summary, so then there will be monthly executive summary. So apparently October month still not available, but September month is available. So I'll open the September month executive summary. So here you will find authentic or whatever, the Government of India Ministry of Power CEA executive summary on power sector. So this is a very useful resource. So let's spend some time going through what this is. And of course, it will also cover our subject today, that is wind. But along with wind, I would like to cover some other useful information that is available in this. Okay, so let's briefly go through this. So first we have executive summary for the month of September, and section A is on highlights of power sector. Section B is on capacity addition, transmission lines, substations, and then generation, power supply position. So many things are there. Rate of sale of power, all these things, and growth of power sector and all. So this is again good information. So for if you want to provide your students with what is the status, so you can do that. So let's first go through this. So first we have electricity generation report. Now in billion units. Okay, so billion units. So 1 unit is 1 kWh. So billion units will be terawatt hours actually. So uh, billion will have I think 9, and then so and let me directly go to the All India. So All India was 110, and then 109 was achieved. So that way, so we are able to achieve the target. So compared to last year, now it is increased the billion units of generation. So that is one thing. Next, the next table also shows electricity generation during April to September and April to September. So this is from the for 1 month. So now here you can see, sorry, from the financial year actually, from April, May, June, July, August, September. So 6 months. So here we notice that the electricity generation is actually less actually compared to last year. So obviously the reason everybody knows because of this corona impact and lockdowns and all. So we the demand also reduced, so therefore the generation also reduced compared to last year. But then the reduction is not too much. It's probably about 10% reduction. So 659 billion units were generated from April 19 to September 19, whereas from April 20 to September 20, 598. It's not much difference, about probably about 10%. Now, if I further go down, so conventional and renewable. So see, having renewable capacity is one thing, and actually generating renewable energy is another thing. So if you notice here, uh, in the month of September, 109.84 billion units were generated from conventional sources, whereas from renewable sources, we are able to generate 10 billion units. So approximately about 9 to 10% we are generating from renewable energy. So the renewable energy share of India is about 10%. Okay, so that is one more point. Okay. So yeah, so when compared to the previous year, so again we notice similar pattern, so where the generation from conventional sources was 105 billion units, and generation from renewable sources is about 10.7 billion units. So this is again this. Now this amount of renewable generation also depends on the month also. So now it is winter season. So particular like summer seasons, you can expect solar power to be more, and like that. So okay, so growth in total generation and all we can see. Now you can also know the breakup actually. So what is the breakup of renewable generation? So wind, solar. So since our session is now on wind, so we can see in the month of August 2020, what is the wind, and in the month of August 2019, what is the wind. So we can see more or less, I mean, it's maintaining. So like that. So solar has significantly increased. Wind. So Mostly right now we can see the growth is in the solar sector, but wind is also kind of growing. So this is generation capacity addition. So this year, unfortunately, there is no capacity addition in generation. So again, we continue. So this is during this thing. So now this is important and interesting slide. So all India installed capacity region wise as on 30 September. Okay. So earlier we talked about generation. Now we are talking about installed capacity. So if you look at this table, uh, the rows indicate the northern region, western region, southern, eastern, and northeastern region. So different regions of India. And we can see how much of thermal is generated, how much of nuclear, hydro, and renewable is generated. So instead of now worrying about regional things, let's look at the all India information. And the same information is also reproduced down in the bar chart. So the green color bar chart is what we should worry right now. So that is the renewable energy generation, renewable energy capacity, not generation. So it is about 89 gigawatts. So renewable energy capacity is about 89 gigawatts or 89,229 megawatts. So it is similar. Whereas the thermal is still dominating, and the thermal is about 231 gigawatt. And total all India installed capacity is about 373 gigawatt. So percentage wise, if you see how much is the percentage. So if you want to know what is the renewable percentage, let me just quickly calculate that. So 89 divided by 373 we have to do. So if I do that, so I'll get the renewable installed capacity of 23.8%. Okay. So 23.8% is renewable capacity, whereas the actual renewable generation is only 10%. Okay. So again, as I mentioned, that gap is expected because of intermittent nature of renewable energy. Okay, so let's see if there is anything more interesting in this. So if you further go down, again installed capacity according to ownership. So earlier we saw installed capacity according to regions, but now here installed capacity according to ownership. Okay, so a lot of people will be surprised to know about this. I mean, typically the students, when we ask them who is the owner of generation capacity in India, I give three choices. One is the central government, next is the respective state governments, and next is the private. And most of the time, students answer that the central government is the owner because NHPC, NTPC, all this nuclear power corporation, all these major power plants are owned by central government. But then, if you actually look at the pattern, right now almost it is central government is actually the least, only 25%, whereas the state governments are at 28%, and private sector almost 50%, so that 47%. And within no time, probably in next 6 months to 1 year, the private ownership of installed capacity in India will become more than 500, more than 50%, sorry, not 500, more than 50%. So right now, 175 gigawatt is the capacity. If I actually go back and look at the plot once again, on the extreme right, we find one black colored bar chart. So that is captive power plant. Now, this captive power plant also is very significant. In fact, the captive power plant capacity is more than the hydro capacity in India. So, what is the captive power plant? It is about 55. Here you can see it is about 55 gigawatts of captive, which is not counted in the total. So, what is so let's say there is a cement factory or a paper industry or whatever. So all that factories and industries, they have a backup generator. So this backup generator is called captive power plant because whenever there is a interruption, so these backup generators will be fully utilized by those companies. Okay, so the captive power plant uh, capacity is significant actually, which is so most of the time it is private. So if you actually add this, definitely the private ownership will exceed more than 50%. Okay, so already some interesting things that we come across. So one is the total installed cap. I'm just summarizing. Total installed capacity is 373 gigawatt in India, out of which 89 is renewable energy and 231 is thermal, and others are as shown in the screen. Percentage wise, renewable energy is 23.8 in installed capacity, whereas 10% in energy generated. So, as installed capacity increases, generated.
Sir, now please unmute yourself and you can speak, sir. Hello? Hello? Hello, sir? Sir, please unmute yourself and speak, sir. Hello? Hello, sir? Hello? Hello, Pradeep, sir? Hello? Hello? Sir, please unmute yourself and speak, sir. Sir, please unmute yourself, sir. Please unmute yourself. Sir, please unmute yourself. Sir, please unmute yourself, sir. Pradeep, sir. Hello? Pradeep, sir, please unmute yourself, sir. Sir, please unmute yourself. Pradeep, sir. Hello? Hello, sir. Please unmute yourself. Hello? Hello? Pradeep, sir. Hello? Hello, Pradeep, sir. Jay Krishna, sir.
Sir.
Sir, unmute అయిపోయింది. సార్ స్టక్ అయిపోయింది సార్ వీడియో.
సార్
సార్ది. సార్ ఇమేజ్ ఒక్కటే అట్లే వచ్చేస్తుంది అంతే, ఆగిపోయింది.
లాగౌట్ అయినట్టున్నాడు, మళ్ళీ లాగిన్ అవుతాడేమో.
అతనిది స్టక్ అయిపోయింది, అతని ఫేస్ ఒక్కటే మొత్తం ఇట్లా ఆగిపోయింది క్రాస్ గా.
అదే ఇప్పుడు
లాగౌట్ అయ్యండి. అవును,
మళ్ళీ లాగిన్ అవుతారేమో.
ఓకే సార్. Pradeep sir, is it audible to you, sir? Pradeep sir. Hello? Hello, Pradeep sir.
Sir, Pradeep sir, unmute yourself, sir. You are muted. Mute yourself.
Sir, is it audible to you, sir? Pradeep sir. Pradeep sir, please unmute yourself, sir. Sir, Pradeep sir. Pradeep sir, please unmute yourself, sir. Sir, Jay Krishna sir. Sir. Hello? Sir, Jay Krishna sir.
సార్
సార్ ఒకసారి సార్ ఫోన్ చేయండి
సార్
సార్.
అన్మ్యూట్ చేస్తుంటే మళ్ళీ మ్యూట్ అవుతుందంట అదంతా కదే.
అది సార్ మొబైల్లో చెప్తున్నాడు కదా ప్రజెంటేషన్.
లేదు సిస్టమ్ కూడా ఉంది.
సిస్టమ్ లా పవర్ లేదంట సార్, చెప్పాడు కదా స్టార్టింగ్ లో.
రెండిట్లోనే ఉన్నాడు. రెండు అన్మ్యూట్ చేయండి.
Hello, I think now I'm able to unmute.
Yeah, sir. We are hearing you, sir. We are hearing you.
Okay. So what happens is anytime I press this unmute, it's again becoming mute. So anyway, so I think I'll continue where I left off. So the last point I was discussing was about. So I'll begin by sharing the screen.
Okay, sir.
Yeah, so I was briefly discussing this what I call this document. So this is about transmission line.
Hello, Pradeep sir. Hello. Hello, Pradeep sir. మళ్ళీ లాగౌట్ అయిపోయినట్టు సార్.
నేను కాల్ చేస్తాను.
ఓకే సార్.
సార్ ఇది ప్రాబ్లం.
హలో సార్.
చెప్పినారు సార్, వస్తారు.
సార్ జాయిన్ అవ్వాలి. అదే అదే. And all the participants, please mute yourself. Please mute yourself. And whenever there is a need, when speaker asks you to unmute yourself, please unmute and don't make any other disturbances.
Mallikarjun sir, make Sir as presenter.
Cheshna, sir. I have made him a presenter.
Yeah. So extremely sorry for the interruptions. So
Sir, no problem, sir. No problem.
Yeah. So I was not aware that the call got interrupted. So I was
Fine,
continuing.
Sir. Okay, I have made you a presenter, sir. Now you can share your screen.
Yes.
Okay, sir.
Yeah. So I was discussing about this T&D losses. Again, the same power sector scenario overview I am discussing. So in the
Screen is not visible.
Hello, Pradeep, sir. హలో సార్, హెచ్ఓడి సార్. హలో
సార్
సార్, ఒకసారి ఫోన్ చేయండి సార్. సార్ది మళ్ళీ ఇంటరప్ట్ అయింది.
Hello.
సార్.
Yeah, so hello again. So let me try once again. So
Yes,
in
sir.
case if we are getting some problem, maybe I take some break and then go to a different, maybe go back to my home or something, and then I'll try. So it may be about a 15-minute, 20-minute break if required.
Okay.
So we will do that. But meanwhile, let me continue.
Okay, sir. Done.
If I get disconnected, just call me.
Okay, fine, sir.
Yeah. So this is I was talking about
Installed capacity in India, sir. Hello, Pradeep sir. Hello. Hello, Jay Krishna sir. Sir,
Sir may
sir,
be sharing the document, sir.
no sir. ఏదైనా ఇంటరప్షన్ వస్తే ఒకసారి కాల్ చేయమన్నాడు, ఒకసారి ఫోన్ చేయండి సార్. ఐ థింక్ సార్ ఈజ్ నాట్ ఏబుల్ టు హియర్ అస్.
డిస్కనెక్ట్ అయితే చేయమన్నారు. ఇప్పుడు సార్ లైన్లోనే ఉన్నారు కదా.
అవునవును.
లైన్లోనే ఉన్నారు, షేర్ చేస్తుంటారు.
ఓకే. Sir has moved out of the session, sir. Now you can call him once.
కాల్ చేస్తాను ఒకసారి.
Okay, sir. Hello.
Sir, Mallikarjun
Sir,
sir.
చెప్పండి. Sir.
There is some interruption in the internet for the sir.
Okay.
And he is
Okay.
arranging some other alternative. So
Fine.
give 10 minutes break for the participants, sir. After 10 minutes,
Okay.
we will continue the session as usual.
Fine, fine. So sorry for the inconvenience caused. So all the participants, please be patient, and we are going to start the session again at 10:55 a.m. So please join the session and have a break for 10 minutes.
Hello.
Hello, sir. Hello. Sir,
Yes,
sir,
yes,
it is audible to us, sir.
yes, yes.
Okay,
So
fine, sir.
I was able to switch on my laptop. So hopefully now the interruptions may reduce or
Okay,
maybe
fine, fine. Fine, no issue, sir. I have made you a presenter. Now you can share your screen.
Okay, okay.
Fine, sir. Yeah, sir, it is visible, sir.
Yeah. So thank you. So I was discussing this scenario. So I mentioned this that the wind capacity is 38 gigawatt and fourth largest. So from here we went to the particular EA website. CA.nic.in. So this website will give you more information. Now there is another source, that is World Wind Energy Association (WWEA), and the overall capacity of all wind turbines installed worldwide is 650.8 gigawatt. So about 650.8. And as of 31st August, so this point also we just discussed, 372 gigawatt is the all India installed capacity, out of which wind power is about 10% and total renewable energy is about 23%. So that's what is the next session. So 23% is the 23.8% is the renewable energy capacity. Now energy wise, we also saw that energy wise it is about 10%. Now, what is the wind energy potential in India? So again, the next point says India has high wind energy potential. Okay, so let me just make it even more zoom so that you can see properly. India has high wind energy potential, 302 gigawatt at 100 meters and hub height, and 695 gigawatt at 120 meters hub height. Okay, so just by increasing the hub height by 20 meters, the capacity almost doubled. So from 302 gigawatt to 695 gigawatt. Now, what is our target? The Ministry of New and Renewable Energy has set a target of installing 175 gigawatt by year 2022, which includes 100 gigawatt from solar, 60 gigawatt from wind, and 10 gigawatt from biopower, and 5 gigawatt from small hydropower. Here, they are mentioning that we may fall short a little bit on wind energy because right now solar is growing faster than wind, so that might be one reason. So here again, couple of points are there. So total wind energy generated in India for the month of July is 6.9 terawatt hours, that is 6.9 billion units. Whereas in the month of August, it increased significantly to 9.6. Okay? So huge variation of, although the capacity is same, the amount of wind energy variation is different. Now we can calculate what is called as the capacity factor. Okay? So we know that the capacity is 37.999 gigawatt, and capacity is available 24 hours and 3 days. It will be the capacity utilization factor. Whereas for thermal generation, it is almost 60-70%, and in some cases even more. So, are you able to hear? Is it fine?
Yes, sir, it is clear.
Okay, okay, thank you. So now, again, going forward, so in the month of July 2020, the total electrical energy demand met by India is 121 billion units, from which 13.2 billion unit is from renewable sources, out of which 6.966 billion, that's what we saw earlier, is from wind energy. So wind capacity is 23%, while the wind energy consumption is only 5.723%. So this is again one more disadvantage with the wind, because the capacity utilization is slightly less. Okay. Now going down, largest wind farm in India, Muppandal wind farm of capacity 1500 megawatt. So again, I request people to do a Google search on this particular topic. Then you will find more information. In fact, what is the location, how much is the area, all that, what is the connections, what is the configuration, ratings, all the information is available. Second largest wind farm is Jaisalmer Wind Park of capacity 1064, developed by Suzlon Energy. So this is about that. Now, whatever so far we discussed is onshore wind. Now, coming to offshore wind also, the ministry, MNRE, has set a target of 5 gigawatt of offshore wind power by 2020 and 30 gigawatt by 2030. So there is offshore wind power also being generated. Now, Tamil Nadu has nearly 9.3 gigawatt of cumulative wind installation, representing a 24.77 share in the total installed capacity. So the entire information which I presented above is available at this particular link. So you can see that. This diagram shows the evolution of the size of wind turbines. So a single wind turbine, what is the capacity? Okay. So back in 1980, 0.01 megawatt, that means about 10 kilowatt was the capacity. So at the height of 15 meters, a 10 kilowatt wind generation 1980. As we move, instead of multiple small wind power generators, we are going towards one single large wind power generator. Okay. So here, if you notice, the biggest one as of 2020, a single wind tower can generate 20 megawatts of power, and at the height of 252 meters. So in fact, we are going to see the relations a little bit, mathematical part I want to cover. So we are going to see that eventually. So going down, wind power scenario in the world. Okay, so far we have discussed about India. Let's briefly discuss about the wind power scenario in the world. So again, from data from World Wind Energy Association, overall capacity of all wind turbines installed worldwide is about 650.8 gigawatt, and China tops the chart with 236 gigawatt. And United States is 105, and Germany is 61. So followed by India. What is the installed capacity in India? So do you remember? So here I'll mention. So India is the fourth, I think about 39, right? 38 or 39. If I go back. So these are statistics you should remember, so that you get a general sense of how it is going on. So 38 gigawatt. So in fact, by now it is 39 gigawatt. So we can actually compare. So I'll just show you the comparison. So, for example, Germany is almost about double that of India, and United States is about 3 times, and probably China is also much larger. So now, what are the top 10 countries? Okay, so if you see, let me zoom out a little bit so that you can see completely. So this top 10 countries by wind capacity in 2019. So on the right side, you can refer, China is having 36% of the world. US is having about 16.2%, Germany about 9.4%, and India about 5.8% of the world capacity. So we are also nicely picking up. In fact, India's percentage was only 4.3 last year. Now we have become 5.8% in the world number. So this shows a good trend. So okay, so I have so far I have covered this scenario. Next to cover the now. I'll just wait for 2-3 minutes. If you have any questions, let's discuss that. Any questions as of now? So I hope you are able to hear me. So any questions as of now?
Sir, I think there is no questions, sir. You can continue the session.
I'm sorry. Can you repeat? I could not hear.
Sir, you can continue the session, sir. We are
Okay.
hearing you.
Okay.
Fine.
So just give me 2 minutes. I'll change to my writing tab so that it will be possible. So just I'll share my screen shortly.
Okay, sir.
For the time being, just in 2 minutes, I'll come back.
Fine, sir.
Yeah. So I hope you are able to see screen.
Yeah, sir.
I want to use pen tablet kind of thing because I want to discuss something called the mathematical modeling. So let me write it here.
Fine, sir. Okay.
So mathematical modeling of wind turbine. So this is very good source for understanding how the wind turbine works and how it generates the electricity. So here, for ease of understanding, I'll just create a drawing. Okay, so this is like a simple representation of a wind turbine. So it will have a wind turbine like this. So this is the ground, and then this is the wind turbine. Okay. Now, some of the things that you should note here. So let's say what it does. It converts the kinetic energy. Okay, so kinetic energy 1, and the kinetic energy is transferred to the blades, and the blades rotate, and machine rotates, and finally the output will come in the form of electrical energy. Okay, so, or let's call it electrical energy or mechanical power. In fact, I'll write it ME because I'll just refer to as mechanical energy, not worrying about the generator. Okay, so finally the output will be the mechanical. Now, if certain amount of kinetic energy is entering, certain amount of kinetic energy is leaving. Let's denote that as KE2. Now, what is the kinetic energy? So kinetic energy is nothing but half mv square. So because if we see the wind has a velocity, and you can, what is the mass of the wind that is coming? So from that we can find out that. So maybe I'll use the slightly darker green. So let's say the wind here velocity is v1, okay, and here the wind velocity is v2. Okay. So what is the kinetic energy? So it will be half m v1 square. Okay. So this is the kinetic energy. Whereas here the kinetic energy will be half m v2 square. And simply I can write the mechanical energy extracted is nothing but half m v1 square minus v2 square. Now, the issue here is, if I want a maximum value of mechanical energy, I can simply substitute V2 equal to 0. So if I substitute V2 equal to 0, I can extract maximum energy. But that is not possible, because if V2 equal to 0, that means the wind here will be stationary at the back of the wind tower. If the wind is stationary, no further wind particles can come, and therefore there won't be any functioning or energy conversion here. So definitely, so V2 has to be greater than 0. Okay, so I'll say V2 has to be greater than 0. And obviously, if V2 equal to V1, then what happens? The mechanical energy out. So therefore, more than V2. So this is the condition for proper functioning of this particular thing. So input velocity should be more than output velocity, and it has to be more than 0, because if it is 0, then there won't be further flow of wind. Now, then the question is, what is the proper optimal value of V2 such that I can generate the maximum value of mechanical energy? So this is what we are going to analyze now. So any doubts as of here? Any questions as of here? Are you able to follow it properly? Just I want to understand whether you are able to follow the thing properly.
Yeah, it's okay, sir.
Okay. So good. So here, let's also make a note of the units. So here the unit is meters per second, and here the unit is meters per second. Okay, so let's continue. So now I have this expression here, okay? Mechanical energy and this one. So energy divided by time will be power. Okay, so what I can do is I can divide this by delta T, and I can divide this by delta T. So energy uh, so this part will be as it is same, half into m by delta T, and then into V1 square minus V2 square. So what is this m by delta T? So the m by delta T, this quantity has a unit of kg per second, because mass is measured in kgs and time is measured in seconds. So this is called flow rate of air. And usually this is denoted by letter Q. Now, I want to, what is this flow rate of air with respect to this? I want to eliminate the variable m. Okay, so how to eliminate the variable m? So here you can notice. So yeah. So how to eliminate the variable m? So I take what is called as rho a and v. So here velocity is v1. Okay, let me indicate like this. Here velocity is v2. Let me indicate like this. So here let the velocity be denoted as vt. Okay. So at the turbine, the velocity of the air is vt meters per second. And if I take this area of cross section, sorry, I just got just a minute. I think the program got closed. Okay, I think unfortunately we lost the drawing. So not to worry, I'll quickly redraw it.
Fine, sir, no problem.
So turbine like this, and here the velocity is vt, and here the velocity is v1, and here the velocity is v2. And the cross-section area of this, let's call it as cross-section area of A. And rho is the density of air. So what is the product of all these three? Okay, so rho A Vt. So let me just look at in terms of units. Okay. So what is the unit of density? It is kg per meter cube. That is the density. That means mass by volume. Okay, kg per meter cube. Similarly, what is the area? So meter square. Okay, so that is the unit of area. And similarly, unit of the velocity Vt will be meters per second. Okay. So finally, if you notice here, the meter cube is in the denominator, meter square and meter is in the numerator. So all this m will get cancelled, and finally we'll get kg per second. So this kg per second is nothing but flow rate. Just now we were discussing flow rate Q. Okay, and what is the value of Q? So the value of Q, it was what we calculated. That is, no, we actually calculated PM. Into V1 square minus V2 square. So this is what we calculated before. Okay? So now if I substitute, so this flow rate is nothing but m by delta t. Okay? So this one can be substituted here. So finally I'll get mechanical power is half into rho A Vt V1 square minus V2 square. Okay? So now I have eliminated the m from this particular equation. So let's call this equation 1. So the mechanical power is like this. So I'm just saving this file so that we don't lose it again. Okay, so we will continue our, please bear with me, we will continue our analysis a little bit more. Now, I want to further eliminate this Vt and find out the relation of Vt in terms of V1 and V2. Okay? So how to do that? So let me go to the new. Okay, so we all know that so F equal to ma. This everybody knows. Okay? So force is mass into acceleration. So, but what is acceleration? Acceleration is nothing but rate of change of velocity. Okay? So here I can write delta V by delta T. So this is this one. So now we already know what is m by delta t. That is the flow rate and change in velocity. Okay? So that is V1 and V2. Okay? So if you notice this, if I write it m by delta t and then change in velocity delta V. So m by delta t just now we calculated. So let me show. So here you can see m by delta t is nothing but this quantity. Okay. So rho A Vt. So this one will become rho A Vt, and change in velocity is nothing but V1 minus V2. Okay. So this is the force. Okay. Now, what is force into distance? Force into distance is work done. Okay. So what I can do is I'll multiply Vt on both sides. Okay. So force into Vt square equal to rho A Vt. I'm sorry, this Vt square will not be there. Equal to rho A Vt square into V1 minus V2. So this is work done. See what is force into velocity? That is work done per time. That is power actually. Okay, so force into velocity is power. So therefore, so this is also equal to Pm. Okay, so now if I take this as my equation number 2. So if I go back, so equation number 1 is here. That is Pm is half rho A Vt into V1 square minus V2 square. This is equation 1. Let me see if I can copy this. Okay, so again there is a problem. So I'll just go for a new file. So by equating Pm from both the equations, so let me write it here. So Pm is equal to, we got on one place we got half rho A Vt into V1 square minus V2 square. So this is from the change in the kinetic energy. And one more equation I got, Pm is equal to rho A Vt square multiplied by V1 by V2. Okay, so these two are equal. Okay, so these two, so this is equation 1 and this was equation 2. So now by equating these two, I can write half rho A Vt V1 square. See this V1 square minus V2 square, I will write V1 plus V2 multiplied by V1 minus V2. So this will be equal to rho A Vt square V1 minus V2. So from both sides, I can cancel out V1 minus V2. I can cancel out A. I can cancel out rho. And then I can cancel out 1 Vt. Okay, so the square term is there. So here directly I'll get Vt equal to V1 plus V2 by 2. Okay, so this is again very intuitive and very interesting finding. Okay, so what we got here is that again I draw the small turbine. So here wind velocity is V1, here wind velocity is V2, and in between the wind velocity is Vt, and mathematically this is nothing but average of V1 and V2. Okay. So this is what we proved mathematically, that let's say here if it is input wind is 20 meters per second and the output wind is 10 meters per second, then at the turbine the wind velocity will be 15 meters per second. So like this we can do that. So this is first finding, but this is not sufficient. Okay, so what I want now is to maximize the PM. So how to do the maximization of PM? Okay, so now that I know Vt in terms of V1 and V2, so now I can maximize. So let me go back to this first equation. So this one I will take. So now PM is equal to half rho A. So in the place of VT, now I'll substitute V1 plus V2 by 2 and V1 square minus V2 square. Like this I'll substitute. So this one little bit of simplification. Rho by 4. Okay, so 2 into 2 will be 4. A will be area of cross section. And here V1 square, V1 cube it will be, and minus V2 square V1 plus V2 into V1 square minus V2 cube. So just I've expanded PM. Now how to find the maximum of this value? So simply we have to do differentiation and equal to 0. Okay, so here one thing I forgot to mention. So if I go back to this diagram, so V1 is not a controlled variable. So this is uncontrolled variable. So this is defined by weather. So if the weather is windy, then the V will increase, and if the weather is calm, then V will reduce. So this is not under our control. Okay. So whereas V2 is under our control. Okay. So this we can control. Now how to control V2? How to control? Simply, so the blade, if the blades are rotated such that they are not obstructing the wind, then V2 will be more. And if the blades are rotated such that they are more obstructing the wind, then the V2 will be less. So by controlling the pitch angle. So by controlling the pitch angle, I can control the value of V2. So because V2 is controlled variable, I can go for the differentiation of PM with respect to V2. So this is a constant, rho A by 4 is a constant. Now here differentiate with respect to V2. So this will become 0 and this will become minus 2V2 V1, and this will be V1 square, and then finally this will be again 0. Okay. Now if we differentiate it and equate to 0, then this term this term cannot be 0, so therefore this term will be 0. Therefore V1 square will be equal to 2V2. Okay. So from this, I'm sorry, this is V2, right? I'm sorry. So I just minus 3V2 square will come here. Okay. So finally I'll get a differential equation. So let me see, note this point, minus 2V2 V1 plus V1 square minus 3V2. So this is a differential equation, quadratic equation. So if I go for a new file, so I'm getting a quadratic equation something like this, minus 2 V2 V1 plus V1 square minus 3V2 square equal to 0. Okay, so again, apologies for all this mathematics. It is interesting. This I'll just multiply by this thing, 3V2 square plus 2V1 into V2 plus V1 square equal to 0. Okay. So finally, this is like a differential equation. Now I can divide both sides with V1 square. Okay. So divide by V1 square, divide by V1 square, and divide by V1 square. And this side also divide by V1 square. Okay. So then I'll get 3 into V2 by V1 whole square plus 2 into V2 by V1. So this will be like a quadratic equation. So this will be 1 equal to 0. So finally, 3a square plus 2a plus 1 equal to 0. So if you solve this differential equation, so you will get a equal to -1 or 1 by 3. Okay. So obviously -1 is not possible because A is V2 by V1. So if A is -1, that means we are reversing the wind, which is not possible. So therefore, this answer is not valid. So therefore, A is 1 by 3. So therefore, what is the condition for maximum power? So this is basically MPPT. Condition for maximum power is that V2 by V1 should be 1/3. Okay. So in other words, if the input wind velocity is let's say 12 meters per second going to the wind turbine, you should define the pitch angle in such a way that the output will be 4 meters per second. So then only you can extract the maximum power from the wind turbine. Okay. So this condition. Now we also have the expression for maximum power, right? So what is PM? So PM is again half rho A VT. VT is nothing but V1 plus V2 by 2. And then finally here, V1 square minus V2 square. So here, if I substitute V2 equal to 1/3 of V1, then I will get the PM as a function of only V1. So finally, we will notice, I mean, because of the lack of time, I am not going into details. So we will notice that PM will be proportional to V1 cube. Okay? So this is the particular information we get. Whatever is the wind velocity, the mechanical power will be proportional to the cube of that wind velocity. Okay? So again, enough of mathematical thing. So I would like to pause once again. So any doubts you have so far? So again, for the STTP program, sorry to bother you with all these mathematical things, but I found it was interesting. So I thought I will share this with you. So any doubts up till here?
Sir, we are clear with the details, sir. You can continue.
I'm sorry, I could not hear. Can you repeat?
Sir, we are clear the session.
Okay. So yeah, so if there are no further details, let's go back and spend some time just analyzing some of the wind turbine data sheets. Okay, so I believe I'm still sharing my sheet. So okay, so what I've done is I've gone to Google and then randomly I just searched a wind turbine data sheet. Okay, so let's look at some of the wind turbine data sheets. Okay, so this is one example I'm getting. I think I'm getting. So here is the data sheet. Now, so here our output is 3.5 kilowatt. Okay. And the area is 12.6 and blade diameter is 4. So all this information we can use to actually validate whether it is developing maximum power or not. So that is the purpose I showed the. I'm sorry, is there any doubt?
Sir, no doubt, sir.
Okay, okay. So you can see some of the things, and here you can see the rated things. Wind speed meters. Braking wind speed is 22. Braking means more than 22, it cannot withstand, so it has to be stopped. So RPM at rated power is 350 RPM. So it rotates very fast because it's just low kilowatt, 3.5 kilowatt. And survival wind speed and then survival RPM. Next, inverter also they have mentioned. So because I think they have an inverter to convert the output to AC. So grid power, so 3 to 12, and then as the wind speed increases, the power output increases to the power of 3 actually. So that also you can see, and annual energy production we can see. Okay, so this is a particular company in Canada. Okay, so let me go back. There is one more source. I'm just opening once again. Okay, so again in your free time, please do the following. You can download a lot of data sheets of wind turbines, and you actually look at their specifications. So now from 3 kilowatt we are going to 3 megawatt. So almost 1,000 times bigger this particular thing. So it is very big thing. 3 megawatt is very big. And so all the details, 27-page complete details are given. So let us go to yeah. So the general specifications. So again here you can see so three blades, and then the power control is by pitch control, and it can operate at variable speeds. Exactly the same pitch control which I mentioned. So what do they do in the pitch control? They try to control the pitch angle such that whatever is the wind speed, see for example rated wind speed 12.5. So let's round it off to 12. So if the input wind speed is 12 meters per second, they will control the pitch such that the output wind speed is only 4 meters per second, 1/3 of it. Then they will be able to achieve the maximum power output, which will be about 3,000 kilowatt or 3 megawatt. So these are some of the details. So it can come in 100 meters height or 90 meters height. So if it is 100 meters height, then with 12.5 meters per second itself, it can generate the maximum power. So here rotor speed is 5 to 16 RPM. So this 16 RPM means in 1 minute it will make 16 revolutions. So which is quite slow because of its huge size. So as the size increases, the rotor speed also decreases. So this is again what kind of generator it is using. So a synchronous machine and water jacket cooling around stator. So air cooling with the air water heat exchanger. So it has a water pipeline across the generator, and it will be cooling. So generation voltage, generation frequency, and then frequency converter. So and then once it generates at 660 volts, the voltage is stepped up to very high voltage, so that 3 megawatt means it should be very high voltage. So it has to have a step up. So power curve is also there. Guaranteed power curve with rotor diameter of 90 and 100. So air density is 1.225 that we already discussed. So and the transformer losses are not included. So then this is the power curve we can have. Okay. So at the initial stage, 3, 4, 5, 6, 7, 8, the amount of output goes to the power of 3. Okay. So, and then afterwards, because of the maximum rated capacity, after 15, they will not operate in MPPT mode. They will operate in the maximum capacity mode. So they cannot generate more than this power. So annual production and all this kind of information is available. Okay. So I think I'll not go further into this. Let's just look at one or two more informations. So let's see, this is one more result I got. Okay, this is coming as a saving, so we'll not worry about that. So we saw 3 megawatt. Now let us look at 2 megawatt. Okay. So although it says 2 comma, it's actually 2 megawatt. So again, the rated speed is same, 13 meters per second, but the diameter might be smaller. Okay. So the rotor diameter is 90 meters. 6,000 meters square. So if I go back to the earlier this thing. So here you can see rotor diameter is 90 meters. Okay. So because the rotor diameter is same for here and there, I think maybe there the height might be less. So let's see what is the height. So the height is only 80 here. So 80, 95 and 105. So at 80 height, you will be generating less. Okay. So like this, you will get some information. Oh, good. So they have also given a power curve. Okay. So this orange color plot is the amount of power output. Okay. So as this will be, the curve will be with respect to the cube. Okay. So for example, from 4, if I double, see at 4, what is the power? 93 kilowatt. At 8, the power is 884 kilowatt. So 93, if you round up to 100, so it has increased to 8 times. Okay. So the speed is doubled from 4 to 8. Power is doubled 8 times. That is 2 cube. Okay. So like that, we can see the relation. And again, once it reaches the maximum capacity 2 megawatt, then it is not allowed to generate more than that, even if the wind speed is more. So like this, you will find a lot of sources. So Indian company, I think Suzlon is one of the examples. So let's quickly once go to that and then. So this is again Suzlon company. I think this is based in India. So the manufacturing happens in India, but they have installations all over the world. So here you can see the swept area is increasing and the power output is also increasing. 2.1 megawatt platform. So here we can see again an interesting picture. Okay. So this is called nacelle, and what is inside the nacelle? So here we can clearly see the mechanism for controlling the pitch. So you can see the rotation here. So by rotating this, we can control the pitch angle. And there is a generator here. You can see the generator also, which will it will be like an induction generator. So the output will be AC, and the power electronic converters, and also the transformer is there to step up the particular output. So all of the details we can see in this. So asynchronous induction generator with 6-pole DFIG, doubly fed induction generator. Yeah, the power curve is also given. So wind speed also given. Technical specifications are given. So my intention is, whenever you want to study about wind energy, so just like before buying mobile phone, you compare the different features of different mobile phones and then finally decide which phone is better. Similarly, you purchase a laptop, you do the same. So like that, before thinking or working in the area in wind turbines, it will be better to study the data sheets of at least 5 to 6 good company wind turbines, and from that you can make some interesting conclusions. Okay, so again, is there any final? I think last 10 minutes I'll give it for any final round of questions if anybody is having. So as I mentioned, today we looked at the introduction, mathematics of wind energy, global scenario, Indian scenario, and some concluding remarks regarding the wind turbines. Okay. So any questions you have?
Sir, no question, sir.
Hello. Yes.
Sir, no question, sir.
Okay.
You can continue with your question.
So if there are no questions, maybe I'll just conclude in 1 or 2 minutes. I just want to once again mention that in my YouTube playlist, there are good number of resources available further. So you can again refer to this, and you can see that. So if there are no further questions, then maybe I'll conclude the session. So once again, thank you for giving me this opportunity. I apologize, there were some technical difficulties at the beginning, but then once the power came back, so I was able to log in through my laptop, and I can present without any interruption. So if nothing else is there, can we conclude the session today?
Yes, sir. Fine, sir. Sir, thank you for sharing the information regarding the wind energy resources and also the generation of conventional resources today. And you have presented the mathematical modeling also, as it is very useful to us in doing research regarding this wind energy resources. Thank you, sir. Thank you so much for sharing an excellent and relevant information about the wind energy resources and its importance, how it is going to country. Fine. Thank you, sir.
Thank you. Thank you. Thank you very much.
You have also shared an information regarding the installed capacity in India with respect to the different generating power plants, evolution of wind turbines, mathematical modeling of wind turbines, and also you have given the structure of wind turbine data sheet, per curve, technical specifications, and also the mechanism of controlling the pitch angle in case of a wind turbine by having a presentation with the help of a whiteboard. So it will be very useful for us in doing research regarding the concept of wind power. Thank you, sir. Thank you for sharing such a relevant information about the wind energy sources. Thank you for readily accepting your invitation and delivering the lectures for today's session, sir.
Yeah. So thank you. Thank you.
Thank you, sir. Thank you so much. So participants, as the session has been ended for today, you can join the session in the afternoon at 2 p.m. sharply.
So please join the session at sharp 2 p.m. in the afternoon. I am going to end the session for today.